So yeah, this is the last presenting order, and I'm happy to be a last presenter. So I hope you enjoyed the conference. So let's get started. So when we think of a camera, we usually think of capturing images like this video. Each frame records the brightness of the scene. But what if, instead of recording the brightness itself, a camera only measures the temporal changes in brightness? In fact, there is a special type of sensor called event camera that exactly does this. Here is a side-to-side comparison. Notice that the event camera does not capture the full images. It only reports brightness changes, emphasizing motion in the scene. So how does event camera work? Event cameras uses a specialized sensor called dynamic vision sensor. Each pixel continuously monitors brightness L, which is log of intensity, and stores a reference value. When the brightness change exceeds a certain threshold C, the pixel generates an event and updates the reference value accordingly. Brightness increase produces a positive event like this, and brightness decrease causes negative events like this, and so on. Event cameras offer several advantages over standard cameras. First, extremely high temporal resolution for capturing fast motions. Second, very high dynamic range that works well under the challenging lighting conditions. 3. Low power consumptions because they only measure the brightness changes. These advantages have led to growing interest in event cameras across many applications. To develop and evaluate algorithms for these systems, we also need accurate simulators. The goal of event camera simulation is to render a sequence of images over time and reproduce the event triggered from these images. However, many existing simulators assume noiseless rendered inputs, often relying on rasterization, which is fast but not physically accurate. Instead, our goal here is to enable the physically based event simulation using Monte Carlo rendering. However, as you know, Monte Carlo method often requires a lot of samples to get a noiseless image. Unfortunately, this is even more challenging for event camera simulation, which requires much higher frame rates and measures much smaller difference signals, which inherently has lower SNR, leading to a much higher sample budget than standard RGB rendering. Therefore, making the simulation low SPP is very important for event camera simulation, but if we naively use this noisy input, its temporal noise triggers a huge number of false events throughout the image. Recently, several methods have been proposed for low SPP input event simulation, including adaptive denoising, adaptive sampling, and spiking neural networks. However, they still require tens of samples per pixel, making efficient event simulation challenging. In contrast, our method, namely event SVGF, based on real-time rendering technique, operates with only 2 SVP, allowing to suppress false events while preserving true temporal changes, even with very low sample budget. Before discussing the algorithm, let's first define the problem. Our goal is not to reconstruct the primal brightness value itself, but to accurately estimate the temporal brightness changes. So one might ask, why not simply render the brightness like standard cameras and generate events from it? While this is possible, event cameras are primarily driven by high-frequency temporal signals, not guaranteeing low-frequency accuracy. Let's look at this example of GT brightness signal change over time. If we reconstruct this brightness signal from occurred event, it often undergoes low-frequency drift like this, which indicates low-frequency component is inherently ill-posed for event camera sensor. So, event camera is accurate in capturing delta L, high-frequency components, but not for L, low-frequency components, which justifies simulating more focusing on delta L. Theoretically, this high-frequency temporal accuracy is closely related to false event suppression in simulation. Think about this GT brightness change over time, and the red curve here is the Monte Carlo estimate, which has high-frequency noise like this. And due to its temporal instability, it causes many spurious threshold crossings and thus false events like this. In contrast, the second signal has a similar brightness error but is much more temporally stable, resulting in far fewer false events. So our main objective is not to minimize the brightness error itself, but to accurately estimate this temporal brightness changes. So our proposed method, event SVGF, is designed to accurately simulate brightness changes. The method consists of two key components, correlated sampling and difference-aware denoising. Next, I will explain each component in more details. First, let's look at correlated sampling part. Our goal is to estimate the temporal difference signal. And the variance of this signal depends on the correlation between the two frames. By increasing the correlation between consecutive frames, we can significantly reduce the variance. In fact, exploiting the correlation between samples have been widely studied in gradient domain rendering through a technique known as shift mapping. The key idea is to estimate the image gradient by subtracting two highly correlated paths, namely base path and offset path, that have similar path throughput. Several implementations are possible, but in this paper, we use random seed reuse that use same random seeds over the consecutive frames. Here, we compare the independent sampling and correlated sampling using random replay at 1 SPP. And as you can see, correlated sampling substantially reduces the noise in the brightness difference, but it seems like we still need further denoising. Now let's discuss the denoising part. To further reduce the noise and the brightness changes, we built upon the SVGF pipeline. I will skip the detail, but SVGF is a real-time denoiser based on edge-avoiding Atrous wavelet filtering. In fact, one of the previous work have already shown that SVGF can be used to estimate the temporal gradient in Monte Carlo rendering. So why don't we just use this? Actually, there is an important distinction in the context of the event cameras. So previous methods typically considered this motion-compensated temporal differences, where corresponding points are matched across frames using motion vectors. This reduces variance, so this is desirable in lots of standard rendering tasks. However, this is not the case for event camera. Event camera does not work in this way. So there is no explicit motion compensation for event camera, but it simply responds to the change in brightness observed at each pixel. As a result, we must estimate the non-motion compensated temporal differences, which requires modified denoising process. To address this issue, we propose a difference-aware edge stopping filter. So consider this simple example where the square moves towards the lower right direction. The resulting temporal difference will look like this. If we denoise this signal only using information from the current frame, the difference region tends to be blurred by the filtering process like this arrow. Instead, we incorporate the information from both current and previous frames when computing the filtering rate. So implementation is quite straightforward. We just replace the edge stopping weight with the product of weight computed from the current and previous frame features. We will not go into the details here, but several other components of the SVGF pipeline also need to be modified. In particular, we modify operations such as albedo demodulation and temporal accumulation to make this process difference-aware. Finally, we need to adapt all components to operate in log intensity rather than intensity itself, since the event camera responds to changes in log brightness. So I'm going to skip the details again. So here is the full pipeline. We first generate demodulated difference image with correlated sampling. Then we perform temporal accumulation mixed with history difference values. We also perform spatial filtering using the proposed difference-aware filtering. Finally, we reconstruct brightness change and generate event accordingly. Now I'll show some results. We simulate these scenes with camera moving forward and visualize temporal changes in intensity, brightness, which is log intensity, and also resulting events. So here we compare several different rendering methods under equal time budget. And as you can see, the naive path tracer without using any filtering or denoising, it ends up with huge amount of noise in the difference images. Using correlated path tracer without any denoising itself improves the result. But as you can see, it often suffers from abrupt change between the two samples, which causes fireflies like this. Primal RGB image denoising algorithms like optics denoiser or SVGF gives satisfactory result in primal domain like this, but when we evaluate the difference, we can see lots of artifacts like this due to their incremental independent sampling process. On the other hand, our proposed method shows much better result in terms of brightness difference and also suppressing the false event. We show results for other scenes. And here we also show the demodulated difference excluding the effect of the texture. We also analyze the false event rate under the different event threshold. And here, we could observe a clear linear relationship between the false event rate and temporal stability relative to the threshold site, highlighting the importance of reducing noise in temporal differences for reliable event camera simulation. And as you can see across all of the settings, our proposed event SVGF consistently achieves the best performance. Here, I also show the visual result. I think it is a bit hard to notice here, but as you can see, like proposed method work most reliably close to the ground truth value. It would be better if this room was dark, but okay. We then perform temporal analysis by plotting brightness over time at certain pixel. First, the naive path tracing, as you can see, end up with extreme temporal noises. Correlating path tracing improves this noise, temporal noise, but as you can see, it suffers from some abrupt changes like this. Primal domain denoisers like optics or SVGF gives more accurate brightness values, but as you can see, it still is temporally noisy. On the other hand, our event SVGF achieves the most temporally stable result. So of course, as you can see, there clearly exists the low frequency drift. But as I said before, real sensor also suffer from this kind of low frequency drift, and low frequency accuracy was not in our interest. In practice, this low frequency accuracy can be improved via complementary filtering with RGB sensor, with algorithms such as screened Poisson equation or Kalman filtering. But again, still accuracy in the high frequency component of our algorithm is still helpful for such complementary filtering process. We also show frequency analysis of brightness signal. And as you can see, the proposed method achieves the best result, especially in the high frequency region. To show the importance of each component of the denoising pipeline, we perform evaluation study. First, we disable the correlated sampling, and this gives increased noise and some ripple-like artifacts. Then, we disable the difference-aware filtering, and as you can see, it gives blur over the edges. We also show results without temporal accumulation and demodulation, and overall, you could see that the proposed full method gives the best result. Finally, we also compare with one of the previous event rendering method with adaptive filtering. And we found that their method clearly gives better results than naive path tracer like this, but still requires lots of samples, like 128 samples, to be conversed. On the other hand, our event SVGF method gives converse result only using 2 SVP, thanks to power of correlated sampling and tailored difference-aware filtering. So here's the conclusion. So in this paper, we propose a difference-aware denoiser, which is especially useful for efficient event camera simulation under low SPP budget, with help of correlated sampling and difference-aware filtering. So there are several promising directions for future works. For imaging side, modeling hardware noise or developing downstream applications would be interesting future work. And for rendering side, using improved shift mapping, here we only use random reuse, but we can use other algorithms, or using better anti-aliasing algorithms, or using better denoisers like Ribbler, or even searching connections to differentiable rendering can be an exciting future works. So this is the end of my talk. Thank you.
Thank you for the presentation. I was wondering, are your results now better than actual hardware ground truth? Because there would be photon shot noise. Did you experiment with explicitly adding that back after you spend all the time denoising and then add back more like a hardware noise and see if the results are more realistic?
So that's true, but in this project, as I mentioned here, we did not consider like any hardware noise. We mostly focused on the rendering side, like efficiently evaluating the brightness change over time. But as you mentioned, that is a very important aspect of simulating event camera. So yeah, I haven't tested with like adding shot noise after rendering this, but yeah, that would be definitely interesting future work, I think.
Okay, thanks.
Yeah.
Yes, so thank you for the talk. I see that you're showing when, as an example, the temporal, let's say, motion alignment thing with actually a figure from gradient domain path tracing. Could you maybe explain like the difference between this type of task or your method with like temporal gradient domain path tracing?
You mean this slide? Yeah. So yeah, this is very similar to temporal domain gradient path tracing. We also use like random primary space, random seed we use in primary space. But as I said before, the critical difference between this work and our target task is that we need to consider the non-motion aligned version, because event camera, there is no such kind of like motion compensation. It directly measures like naive pixel by pixel like brightness change over frames.
Yes, but like, what is the end goal? Is the end goal still to render the RGB image, or is it to render the difference image?
Sorry?
Like, what is the end result of the algorithm? Is it still
end result of algorithm is rendering difference. We are not interested in private RGB image.
All right, good, thank you.
All right, that brings us to the conclusion. Let's thank all of our session speakers.